Okay, my name's Harry Dawson. This is the Flight Dynamics Lab Albatross UAV. This is the weight and balance. So this is the estimated CG and the real CG. Estimated CG was through the moments created through the axle of the starboard port axle and the nose gear. There's an offset of 0.02 seen in the graph. The safe limit 0.156 and after the leading edge of the MAC and the full limit is minus 0.38. Static tests. So numerous points were measured against a scale, and the scale measured the force that was associated with the percentage thrust, as shown in this graph. This is the static control response. So here we've got the ailerons and the elevators and the rudder. Ailerons doing the roll, rudder doing the pitch, and the elevators doing the pitch. And the rudder doing the yaw. As we can see here, when the ailerons move correctly, they cause a roll. Same, and then yeah. So when the elevators move, we get a roll, as we can see soon. There we go. We see through the arrows. So basically, we see it through the arrows, really. So yeah. So here's the elevator angle. Change the elevator angle, we change the pitch, so we change the relative angle of attack that comes onto it. Maybe see that there. Here is the trim angle. So when we change the trim angle one way, we get the opposite sign for the angle of attack. This is how it should be. You can see that through the plot at the bottom down here. Okay, so this is the pitch response to the function of wind speed. We see it for three different wind speeds that correlate to the minimum, cruise, and max, or the stall. So yeah, the stall is the minimum, the cruise, and the maximum. So the maximum causes a more unstable configuration. We can see this through the large amplitude of the oscillations, and they decrease in size as we reduce in airspeed. Similarly, for the center of mass position, we see, as we see the blue line, when it's placed further back from the mean aerodynamic chord, 50%, we see the largest oscillations, and therefore is very unstable. It was the most unstable configuration. Yeah. So for roll rate, faster airspeeds result in quicker time to complete revolution, as well as faster roll rate. Really. We could see this both through the height and the length of the graph. So rudder reflection on angle slide slip. So we can see here. Yeah, this is how it should be acting. There we go. That's a better video for you. Pitch versus yaw. So we have pitch sees a higher amplitude than a yaw, which suggests that yaw sees a higher amplitude than pitch, which presents that pitch amplitude dampening is higher. We can see this soon. Okay, so this is the effect of the thrust line on the center of mass. So we altered the center of mass vertically along the airplane or the UAV. And then the change in the pitching angle of attack of the UAV between 0 and the max thrust was recorded. As evident from the graph, the CG location is moved vertically downwards and the angle of attack increases. Utilizing the graph, the CG vertical location for zero coupling can be found when the plot line crosses the x-axis, which is about minus 0.018. Next, moving on to the lift curve slope. This is the flight performance of the wind tunnel experiment. It's evident from the graph that CL max at 30 flap is the greatest value of 1.298 at an angle of attack of 10.2 degrees. From 15 flat, max CL is 1.226 at 10.2 degrees as well. and at zero flap has the lowest CL max of 0.993 and 10.62 degrees. When comparing the CL to the manufacturer's value of 1.4, it's very similar. Moving on from this, we have the drag polar. It's evident that flap 30 has the greatest CL values for the specific CD value, followed by 15 and 10. So now we've got the lift to drag ratio to CL. It's evident that zero flap achieves the highest value of 13.64, followed by 15 flap at 13.47 and 30 flap at 11.86. When comparing these values to manufacturer's data of 30, the values outputted from the wind tunnel experiment are much lower. For the longitudinal trim section, the CM, the coefficient, the moment coefficient at the center of mass versus the CL for different elevator inputs was plotted. It can be seen here that the yellow line, 5 degrees, passed through 0. This means the moment is 0 at that particular CL, therefore would be advised. Oh, sorry. It can be seen that through the orange line, minus 5 degrees, that passes through 0. Hold on. No, I was right. At 5 degrees, passes through 0. That means this is the optimal flight condition. Longitudinal stability is here. Basically, we want it to be as flat as possible because it's acting close to the static margin. Ground handling video. So we got the rudder control and the nose gear. It performs pretty poorly. There we go. Minimum unstick speed. So here's the minimum unstick speed. We can see by when in these plots where the lines cross over where the speed is. You can also see, I think it's like 25 degrees. Cruise trim. Oh, this video also shows flaps and no flaps. Flaps, no flaps. Cruise trim. Cruise trim was about 22 meters per second, as seen by that video. Minimum trim, 20 meters per second. Maximum trim, 35 in that ballpark. So Fugoi, we got it's like the long period response. Short period response shown by the spiky bit at the beginning, the large amplitude, and then it's got a long response. So this is the flight video. This is skipped through just because we're running out of time. 20 meters per second was the aim, below 30-meter altitude, and it was fairly trim. You can see that like through here. So yeah, thanks for listening.